right. Good morning, everybody. Welcome back to Foundations of Computing. Today, we are going to discuss a little bit more in detail iterators. Actually, specifically, we are going to go through the exercise that during the last lecture we haven't been able to solve together. And then after that, I will continue on memory and objects, specifically how objects are implemented in Python. That is part of an advanced lecture, so the content of that part is not examinable, and it won't be part of any of your assessments. Same reminders as last time, just to make sure that everybody also who's listening from home gets them. The mid-semester test results were released at the beginning of the week, and you can find associated posts on Ed. Assignment 2 was also released on Monday. Please, if you haven't started working on the assignment, this is probably a good time to do so. The assignment is due on October 10th and is worth 15% of the mark. Grok worksheet 15 is due on Monday, September 30th. This is due before worksheet 14. It's not a mistake. And it's on the 30th because next week there is going to be a teaching break, which is the mid-semester break. As usual, one fun fact, because we have a short lecture today, about Python. Python has what's called the garbage collector. So this is a program within the program, if you want, of the runtime of Python that manages memory, allocation, and deallocation. Whenever you build objects, your program has a certain amount of memory available. And if you build an object, the program needs to allocate some memory to store the content of that object. And when you're done with that object, ideally you want to return that memory to the system so that you can allocate other objects without running out of memory. So this is allocation and deallocation. It also prevents what's called a memory leak. A memory leak is when you forget to deallocate your memory, and therefore, suddenly in your program, you run out of memory because you have lots of objects that you are not using anymore, and they are still taking space in your memory. So Python does this automatically through this garbage collector. There is another language that uses famous for its garbage collector, which is Java. So they both automatically keep track of your objects and when your objects are still reachable in your program. So if an object becomes unreachable, Python will automatically deallocate the associated memory and return it to the system so that you can reuse it. Other programming languages, such as C++, instead have manual memory management. Okay, so just quickly, a bit of a reminder of brush upon what we mentioned last time about iterators. So we defined an iterator as an object, first of all, that enables us to traverse through the elements of what we call the container. Some of these containers are iterables, such as lists, tuples, or dictionaries. And this is all done in an automated way without the need of keeping track of our counter or index within that particular container. Specifically, an iterator object is defined through this iterator protocol, which involves the definition of two specific core methods. One is the iter method, and the other one is the next method. What the iter method does is to return an iterable, and it's not to be called as a member method of that particular class, but directly this general function called iter. So you call iter on an object, and you're expected to get an iterator out of it. If your object is an iterable, that works out of the box. For example, for lists, tuples, etc., all the iterables that we've studied so far. The second method is next. So when we get an iterator, we can call next on it, and that will return the next item in the sequence or raise a stop iteration exception when we finished our container, right? So because this is what defines an iterator, we can use these methods to build our own iterator. So we saw a very simple example last time. Also a quick reminder of the difference between iterable and iterator. An iterable is defined as an object that can return an iterator, not the opposite. And we saw examples, again, always repeating these examples, lists, tuples, strings, dictionaries. You can pass an iterable to iter and get an iterator. An iterator instead is broadly defined as an object that implements the iterator protocol. Okay, with that in mind, we also looked at CSV files briefly. There is not much to know about them other than how to read and how to write to a CSV file. For example, we looked through the reader function within CSV. And so we want now to put a bit what we learned the last time together in a class exercise, as we usually do. So what we want to achieve here is to write a function that processes a CSV file which contains weather data. This is the rainfall data.csv, which, by the way, is available both on the slides here and online. And we want to calculate the total rainfall. I'm going to show the content of that file so that this will be clear. So we want to do that by only by using iterators initially. And then later on, we want to modify our function to actually implement an iterator that does it for us. Okay? So we're going to go through two steps. Here is, as usual, the kind of data we are working with. This rainfall.csv, the header contains all the labels for each one of the columns. The first one is the city, the other ones are months. And then for each row, we get the name of the city at the beginning, and then numerical data associated with the millimeters of rain that we get for that city every month. And again, we would like to process the file, get a dictionary essentially, where we look up the city and we get the total millimeters of rain for that city for the whole year. Okay, so let's do this relatively quickly because this should be a simpler exercise. So the first thing to do is to import CSV. And then, obviously, we want to define our function, calculate total rainfall. And we want to provide the file name, which will be a string. And also, we need to define what's our output, right? What are we going to return? And I said already, a reasonable object to return is a dictionary. So let's define that here. Let's call it totals. And we have our dictionary here. Now the next step, we have the file name. We need to open the file. And last time, as if I recollect correctly, we did it by using just for. And also on the slides, we did that. But that doesn't close the file. So instead here, let's do it properly. Let's use a context manager. We are going to use the with formalism here. And then we can open our file. So we give it the file name to the open function. And we are going to call the resulting object, which we know being an iterator under the hood now, CSV file. Now I left the second part of the open function blank for a reason. What we are going to do here is to use one of the parameters that we can feed to our open function, which is new line. This is a bit of an interesting thing to know. So what this is doing is telling Python when opening my file not to convert new lines automatically. So why would Python convert new lines automatically? Well, the reason is that new lines are encoded typically in a different way in between operating systems, okay? And so what that means is that, for example, let's say I am on Windows. Let's make it a comment. Windows. On Windows, new lines are encoded this way, where actually that, So where the /r is a carriage return character, okay? While in Linux, we have seen that these are encoded in Linux by using just /n. So if my file is coming from Windows, most likely those new lines are encoded as /r/n. If they are on Linux as /n. Now the open function deals with that automatically for you. And that is why so far we haven't provided this argument. The issue is then when you use the CSV module, the reader of the CSV module wants to deal with this by itself. So the reader function is built in a way that it will deal with new line conversions for you. So the next step here that I was going to do so that you can understand this is to create a reader object, which is an iterator, and then use CSV reader and then give it my file. Now, what's the issue here in light of what I just said? CSV reader here wants to deal with new lines. But if I let the open function deal with new lines, I might get that done twice, which can cause problems, and typically can cause format problems such as, for example, adding or removing new lines within your CSV file. So when you're using CSV, just let the CSV reader deal with it because that's the intended behavior. And all we're doing here is to say to the open function, don't touch the new lines. CSV reader is going to deal with it. Okay? This is even more important when you are writing to a CSV file. Okay, so now we have an iterator, right? So we know that this is an iterator object. We have discussed the last time. Oops. iterator. What do we do next? Well, we don't need the header, right? So, but just because we don't want to throw that information away, perhaps we can store it somewhere. So let's call a variable headers. And now we can call next on our reader. So that will give us the header and proceed to the first line, which is where our data starts. And so this will allow us to skip header information. Once we're done with that, we can simply iterate for row in reader. And then the first entry here in row is the name of the city due to the structure of our file. And then we have all the remaining, so from the second entry up to the end, we have data for rainfall. So what do we do with that? Well, let's call it monthly data. And because we want to sum these things, they are at the moment in the file and in a format of string. We want to convert all of them to floats, to floating point numbers. So to do that, we can use our map function, right? So here we get row, we use a slicing, so we can get all the remaining components, elements in our list. And then here we need to provide the function float, or convert all of them to floats. Nice and easy. At this point, we're ready to add to our map, which I called totals. We can provide the name of the city, and we can sum over the monthly data. Okay? And then we can return our totals. Now, how do we use this? We need to use this function. So let's create an object which will give us which can store our dictionary. So let's call it rainfall totals. And we just call our function on our file name. Which is rainfall.csv. Okay, which I have here. Okay, so that will give us the data in there. Next, we want to print this out, as we've done already often for city. And total, this is a dictionary, so key and value in rainfall totals.items. Yes, it seems. Yep, the syntax will be correct. I'm not sure why it's read there. And then we can do some formatted printing. Sorry?
You're missing an in the line. For city total.
Oh, yeah, there you go. Excellent. And then we can do formatted printing here, which we can grab directly from this line, which we have on the slides, just to make it faster and less error prone. Okay, what are we doing here? We are using f strings, right? Then, and therefore we are printing the name of the city here. Then we are printing the total, and then if you haven't seen this yet, This is just a string formatting. What it's saying is that I want to print that floating point number with only 2 decimal places. Okay, I don't want all the decimal places, I want just 2 of them. And then we can run this. Let me show why. There is a Python thing there. And so we get all the data in the format that we wanted. Okay, so this is just to warm us up. Okay, so that's probably, this is the kind of level expected for your assessment. So for your project 2 and you know, for the final exam. But we go now slightly beyond that. And the idea is here we are reading the whole file, right? And we are storing the whole file in a dictionary, and then we are printing these things out. But I don't want to do that because maybe my file is too large. So I want to define now an iterator that allows me to grab one line at a time, process it, and return directly on the fly the name of the city and the total rainfall for the whole year. So I don't have to store the whole file in memory. So how do we do that? Well, that's where you should help me. So who is going to suggest how do we, well, work with me on how we implement this iterator? Anybody who wants to work on a bit of coding? Or you want me to go through it? It's a Friday morning, 9:26, so people are maybe a bit sleepy yet still. Okay, so let me go through it, and maybe I can ask some questions as I go. So the first thing to do, this is more advanced than what normally you would do, is to define an iterator. An iterator is an object. To define an object, I need to define it through a class, okay? So let's call this object rainfall iterator. Right, tool. Now, as you've seen in advanced lectures, the ones who have attended advanced lectures, the first thing that we need to define always for an object is the init function, because that constructs, builds our object. So let's do that first. Def init. Then this function, as all member functions, always need to have as the first argument self, which is a reference to that particular instance of the object that we are building. Now, what can we do in this init function? So every time we build this iterator, what's a good idea to do, considering what's the task for this iterator? We need to give it parameters, and what do we do with that? Let's say this is stuff that we want to do only once, right? Remember, we have init, then we need to implement the iterator protocol, so we need to have iter, and we need to have next. What we put in init is all the work that we will not put in iter and next. So it's all initialization stuff, by definition. So let's say we give it a file name, right? Which is what we were doing here. So there is all this stuff, right? Which has nothing to do with processing our data, okay? So let's say that we put all the initialization in here. We can create an object called self .csv file. Okay, so this is one of our attributes in our class. And we can open the file with our file name. And as before, we can set the new line to the null string. Okay, that's number one. The other thing that we did earlier was to create a reader object from this one. That's also something that we don't need to do many times, right? We do it only once. So self.reader and then csv.reader, and we give it our CSV file. What else? What else are we doing here only once? So we did this, and then you see before the loop, we can also do this, right? So we can create another, this is self.csv file. We can create another attribute called self.headers and simply call next on our iterator, which is self.reader. Okay, nice. We've done all the preparation work. Now def iter, providing self. What do we return here? So this time as well, we are defining our object to be an iterator itself, okay? Once again, we don't have a need to do any conversions or strange other things. All we need to do here is to return self. And then the bulk of the work is going to be in next. Okay? Now, let's go back and see, based on what we have seen earlier, what next needs to do. Basically, next needs to iterate over the rows in our file, right? It needs to store, every time we call it, it needs to give us a new row. It needs to process the row so that we return the city and also the total rainfall for the whole year. Okay. So how do we do that? Well, first of all, and the third thing, once we are done with our file, there are no more rows, we need to raise a stop iteration exception. That's also the other thing that needs to do. So since there is an exception here, we have to use a try except syntax, so two blocks. What do we try? We try to get our new row, and how do we do this? Well, in this case, this is quite simple. We have seen here how to get a row from a reader object. We actually exploit the fact that reader is an iterator itself. So we can do self.reader, and that will give us the next row. Simple enough. Now, what's nice about this is that since self-reader is an iterator, once it does that there are no more rows in there, it will also raise an exception for us, right? And so what we can do is to catch that exception. Stop iteration, right? And what do we do in that case? Well, a couple of things. First one, we close our file, right? Self.csv file.close. The second is we want this iterator to raise the stop iteration exception. So the self-reader raises the stop iteration exception. We catch it. We close the file. We need to re-raise the stop iteration exception because that's what signals whoever is using the iterator that we are done with it. And to do that, we can use this keyword called raise. Raise allows you to raise exceptions. Normally, you would give it the name of the exception here that you want to raise. But if raise is used in an except block, it will raise the same exception as that we used for the except block itself. So this will re-raise the same exception, which is stop iteration, which is what we want. Okay, so now we are done with the except. The normal case is, so we deal with the special case up there. The normal one is, okay, city is just row 0, and monthly data, monthly, oops, I can't spell it, data is instead what we did earlier, map with a float function, and remainder of that row. Okay? And we are basically done, except that we haven't returned it yet. So now we return our city and the sum of monthly data. Okay? How do we use the iterator? We define it, it's an object. So once again, let's call it rainfall iterator. And again, the name of the CSV file, rainfall.csv. And then now, once again, we can now directly loop over the city and the total rainfall data because we have defined the iterator to do that for us. City, rainfall, or actually let's call total in rainfall iterator. And then we can grab this syntax from here and place it here. And we can comment this out so that we don't need to deal with it and see that whether this works or not. And we get the same result. Now, we get the same result, but the big difference is we are never storing the whole file, data in that file. Okay, is this clear? Any questions on this? Again, this is a bit more advanced, so you don't need to do it this way, but it's just for you to know how to do it. Okay, if there are no questions on that, I will proceed next with our lecture, where I want to discuss now, conclude our discussion of how objects are handled in memory. So last time, we left our discussion on this table. And what this table was doing is to summarizing the basic operations that we can perform on different iterables that we have seen throughout the course. We have seen there are many operations here, but what was interesting to observe from this table is that strings, list, tuple, and dictionary all support indexing. Right? In a different way, I guess, because the dictionary you need to use a key, while for the other ones you can use the ID. And then they all support lookup. And lookup, we mean search. So you search for an element within that iterable. Then there is a slicing, and also we asked whether these objects preserve the order of insertion. So as I add elements to that particular object, is it preserving that order? And for dictionaries, this is true only from Python 3.7 onwards, which is what we're using. Now, from this table, there were a couple of observations that I made. First one is indexing for strings, lists, and tuples takes constant time, regardless of the length of my iterable. So if the iterable grows longer and longer, still if I want to access one element using its index, this will take the same amount of time for a short container or for a big one. On the other hand, lookup operations, so searching an element within the iterable, takes linear time. Okay, so the time grows as the container grows. And the reason here is that we essentially need to search through that container. There's no other way, and until we find the element that we were looking for. In contrast, for dictionaries, search takes constant time, which seems a bit of a magic feature because it's so much faster than a linear, right? So constant time means my container grows, but it will take always the same time to access that particular element, that particular value given a key. And so we want to understand why this is the case. And to understand this, we're going to look a little bit more in detail in how these data structures are implemented, starting from strings. So strings are implemented as a contiguous block of memory, as you can see on the, well, for you is the right-hand side of the slide, where each one of the blocks in memory is one character. Okay? Now, strings are immutable as well. We discussed this, which means that once they're created, you cannot change them. Any operation that modifies the string will create a new one. And because of this, since this operation might be quite expensive, Python does some optimization where it's caching the value of strings. So if two variables are initialized to the same string, under the hood, Python might make those two variables point to the same object in memory. And this is called caching or string interning. And it's a bit confusing, but we need to be aware of it. Okay? The reason why this is possible is because of what we discussed about objects during the last advanced lecture. Objects do not simply store the content in memory, but actually what they represent is a reference to that content. So two variables can be distinct, but at the same time refer to the same content in memory. And then on top of that, the strings store metadata such as the length of the string, so we can quickly access it without counting each time how many characters I have. Now, lists. We also had a bit of a look at this a few lectures ago when I myself introduced lists. So here, the idea is that this is a dynamic array, so dynamic collection of references to arbitrary objects in memory. So we have this nice sequence of references to objects. And that's why we can store heterogeneous objects. They don't have to be all of the same kind. Okay? Now the key point is, so because of this, lists are mutable. So you can replace objects, you can add them, you can change their value. All you're going to do is to make one of these references point to another object, to another location in memory. However, what's interesting is that still these references are all stored contiguously in memory. It's one block, one after the other, one address after the other. Okay? And this is why you can access both lists and strings when you do indexing in constant time. Because given an index, I know exactly where to find either the reference for a list to that particular element, or in a string where I have to find that particular character. That's the reason why it takes constant time. Does it really matter how big is this list of references? Because I'm not searching through it. I'm just accessing at the right address. Okay, so dictionaries. Now, dictionaries, we know they are a bit more interesting. So we know that we have constant lookup time for these dictionaries. And I think the most interesting thing here that we need to state is that the keys of a dictionary must be immutable. Now, last time we looked at immutable objects and mutable objects, and there was a bit of a couple of features which were interesting about them. For example, I can have a tuple which has an immutable integer in there and a mutable list. And then I can take tuple 1 and append and this is a legal operation, right? I can print my tuple. However, I cannot use this tuple for defining the key of a dictionary. And what it's going to say is that unhashable. When you want to use immutable types for a dictionary, the key needs to be immutable, including all the objects that that key contains. So it needs to be mutable all the way down, okay? And we're going to see the reason of this. So if I did, obviously, having 2 immutable types in there, then this is not a problem, okay? Okay, the reason why this is happening is that the idea behind the dictionaries is that it's an associative array that stores key value pairs. What that means is that each key is associated with that value in a unique way. This is always called a hash map. Now, how does this work? Each key is mapped to a unique value in the array here. Okay, so given the key, I have a unique relationship between that key and where the address that points, in this case, to the key value pair. This is achieved by using a hash function. A hash function is a function that takes the key, okay, and based on that key is going to produce a unique value, which is an integer, called the hash value. And that hash value can be used to identify the address where we are going to store our key value pair. Now, there are cases where different keys can produce the same hash value, and those are called the collisions. To maintain this unique mapping, we need to deal with collisions, so that there is always a unique mapping between the key and the key where the key value pair is stored. Now, this is the reason why keys must be immutable in dictionaries. If I change the key, every time I take the hash is unique based on that key. If I change the key, I'm going to change the hash value, which is going to change the value in memory, and I lose the unique mapping. So I can't find the key value pair anymore. And here are some of the features of hash functions, desirable features of hash functions, which are the core mechanism of dictionaries. So first, it must return an integer value, which is the hash value. The second is that it must be deterministic. Obviously, you don't want to call multiple times your hash on the same key and get a different value. It should be efficient. We don't want the evaluation of the hash function to take too long because dictionaries are designed so that we can have a very fast lookup. So it defeats the purpose of a dictionary if our hash function is taking of the order of seconds. And then the hash value must lie within a bounded range. What that means is that when we have our hash table, for physical reasons, we need to allocate a certain amount of memory. And that memory has an initial address and a final address. So we want the hash value to be within there, within that range. And that's usually typically achieved simply by doing a modulo operation. Okay? Furthermore, a good hash function should ensure that the keys are evenly distributed in the memory, in the hash table, because that minimizes the chances of collisions. And Python has this built-in hash function that you can play with that guarantees, that has all these guarantees for all immutable data types. But what I want to discuss in the last 2 or 3 minutes is how do we deal with collisions. There are 2 main ways that I'm going to explain today. One is open hashing or chaining, and the other one is closed hashing or open addressing. In chaining, what we do is to, when multiple keys hash to the same value, what we do is to start building a linked list. So we do not change the address. At this address, we make the reference point to a list. And every time a key hashes to this value, we keep adding the key value pair to this list. Okay? So we are using the same amount of memory for the hash table, but we are growing lists every time we have collisions. Now, what's the advantage? It's simple to implement, and technically it can handle with an unlimited number of collisions. The disadvantage is that now, when we look up our value, if there have been too many collisions, so if our hash table is too dense, it has many entries in there, we will end up with lists here. Now, looking up a value into a list takes order n time. So every time I go here, and if I have a list, I need to search in that list to find the associated value. So if there are too many collisions, this kind of hash table gets order n lookup time. So from order 1 might get to order n. In closed hashing instead, what we do, whenever we have a collision, we try to find a free spot in memory for our new value, okay? And there are different ways of doing this. The first one is to, well, this process of finding a new value is called the probing. And there are different strategies for probing. One is linear probing, where I just go next in memory in a linear way. So let's say I have a collision at 1. I look whether address 2 is free. I can put my value there. If 2 is busy, is taken, then I can go to 3, 4, 5, and so on and so forth. Right? Now, the issue with this is that it causes a problem called the primary clustering, where you can imagine that you might get lots of values clustered somewhere in memory. And that slows down also the lookup, because you do probing every time also that you look up, right? So to avoid this, there is another algorithm which is quadratic probing, where let's say I get a collision at address 1, then I look up, instead of looking up 2, I look at the square of that, which is 4. And then I can look at 9, and then I can look at address 16. So that ensures that I leave more space in memory so that I am more and more probable of finding a free spot. So Python, for implementing, well, let's just say the advantage of this is that obviously you have faster lookup when you have few collisions, because you're not looping over lists to search values. It is less memory intensive because you don't build the lists. But obviously, when the hash table becomes denser and denser, probing becomes more and more expensive. So ideally, you want this hash table to be sparse, to have your ideal lookup time, which is constant time. And this is what Python uses. Python uses, for dictionaries, closed hashing with quadratic probing. All right, quickly, in closing the lecture, we have unveiled all these mysteries, say constant time for indexing for strings, lists, and tuples is obtained because they store the values contiguously in memory. Linear time complexity in search is just because you have to search through the container to find your values. There's no other mechanism. While constant time lookup in dictionaries is achieved through the use of a hash map, which is based on a hash function that uniquely maps a key to a specific address in memory that can point to our key value pair. This is also the reason why keys in dictionaries must be immutable, including all their sub-objects that we have in there. And that's pretty much it for today. And I'm happy to take any questions on that. This is a bit of a summary of the last advanced lecture. You can read it yourself. I have pretty much summarized already what we have discussed today. Thanks.